All right, let's get started. Hey folks, welcome to BRK131, how Veeam delivers planet-scale semantic search with Azure Cosmos DB. My name is 𝗦𝗲𝗀𝗀𝗀, I'm the AI product lead in Azure Cosmos DB. Today I'm going to be joined by our friends Zach Rossman, who's the tech lead for AI and security at Veeam, and then also James Nguyen, who's the principal cloud solution architect that has worked very closely with the Cosmos DB team and Veeam at developing and delivering this architecture that we're going to talk about here today. So let's get started. So we're going to start talking just briefly about Azure Cosmos DB for AI, why it's a fantastic database for your AI and search workloads. We'll quickly cover some of the new and exciting releases with regards to semantic search that we had here at Ignite. And then we're going to hand it over to James and Zach to do a deep dive in the next-gen data discovery platform for Veeam. We'll have a sneak peek at a private preview feature for Cosmos DB, and then we'll do a quick wrap up here. So let's start with the question. Why do thousands of companies depend on Cosmos DB as their database for their AI, search, and agentic applications? Well, there's multifaceted reasons here, right? So in Cosmos DB, there's a SQL-like query language that's extremely flexible that allows you to perform complex queries on your document data. And you can do vector, full text, and hybrid search for a full semantic search pipeline right in the query language. Cosmos DB is also designed with multi-tenancy in mind, offering multiple levels of isolation through partition key, so for logical isolation, to collection or database or resource for physical isolation as well. Cosmos DB being a NoSQL database means that it's schema-free. So as your data model changes, as your application evolves or grows, you can change your data model in Cosmos DB. And of course, you can store vector embeddings and your metadata together in the same JSON document to enable your semantic search without needing to ETL your data to another service. It's extremely cost-effective. In fact, if you use Cosmos DB serverless, we like to say that it's cheaper than a cup of coffee to get started, right? You can insert 100,000 vector embeddings from Azure OpenAI, execute 100,000 searches, and it's under $3 for Cosmos DB serverless. But it also has very low latency and high recall for these searches, right? Under 100 milliseconds to end on a billion vectors. Of course, it's highly elastic as we automatically partition and shard your data for you, and also have instant and dynamic auto scale. So as your data size grows, we partition your data. As your throughput needs grow and shrink dynamically with your demand, Cosmos DB also accommodates that as well. And finally, Cosmos DB is enterprise ready, right? Offering up to 5 nines of availability, plus features like geo-replication, multi-region reads and writes, dynamic data masking, and more to support your application securely and robustly, no matter where your end users are. So quickly, let's talk about some generative AI in data scenarios, right? So what we'll hear today from Veeam is how they're using Cosmos DB to store their operational and search data alongside their vector embeddings, right? So this enables them to run semantic search on Cosmos DB without the need to ETL their data into a search engine like 𝗦𝗲𝗀 or a specialized vector database. So they can keep their data consistent and reduce the complexity of their architecture. And then, of course, this unlocks multiple different generative AI and search scenarios like RAG, conversational history, semantic caching for saving and recalling large language model responses, and then, of course, to agentic scenarios as well. And one of the secret sauces to Cosmos DB being extremely effective at semantic search is the Microsoft DiskANN vector index. This is a vector indexing technology that was developed at Microsoft Research and is used widely inside Microsoft, from SharePoint, Microsoft 365, Microsoft Copilot, as well as Bing. If you've ever searched for any videos or images on Bing, it uses DiskANN technology behind the scenes for that semantic search. And starting from the left here, we see that Cosmos DB semantic search with DiskANN is extremely cost-effective. Right? If we compare Cosmos DB serverless with other enterprise-grade service offerings, it's up to 43 times lower query costs for those vector searches. It's efficient at scaling. So we can see that as your data size grows from 100,000 vectors to up to, say, 20 million vectors, right? So we have a 200 x increase in size of the data, but we only have barely a 2x increase in latency. So it scales sublinearly for excellent performance. And then, of course, low latency, even at enormous scale of 1 billion vectors. And at query time, you can tune the accuracy versus speed trade-off. So if you want some search workloads to be a little bit faster, you can do that. If you want some workloads to be a little bit more accurate, you can do that as well dynamically. So in addition to all this greatness for Cosmos DB, like what's new? What are we building actively and releasing here at Ignite? Well, we have multiple new features for vector search, starting with float 16 data type support for your vector embeddings, right? Most vector embeddings that you create from, say, an Azure OpenAI model are float 32s. And if you cast those to float 16s, you can actually reduce the storage footprint of those vectors by 50%. But you take a little bit hit of recall, and maybe that's okay for some of the scenarios if you want to save on some storage costs. We also have performance improvements, enabling 2 to 3x faster vector indexing performance and faster search through advanced filtering algorithms. We're really excited to have a private preview of the Cosmos DB Semantic Re-Ranker, which uses an AI model to re-rank your search results for higher relevance to your queries. There's a QR code and an AKMS link that if you want to sign the form, you can get on the wait list and sign up for our private preview. And then, of course, we're adding flexibility for your containers as well, allowing you to modify your vector indices. This allows you to drop one index for a new index type or change some basic parameters of the index build on the fly. For full text search, we have several new features as well, starting with we're bringing fuzzy search from public preview to general availability, allowing you to have typo-resistant searches in your text data. We're also enabling new languages for the full text index, including Italian, Portuguese, and Brazilian Portuguese that add to our support for German, French, and Spanish, and more languages to come over the next few months. We've improved the performance of full text indexing and our BM25 search scoring for relevance for your keywords and searches. So this will bring a 9 to 10x performance increase on indexing speeds and search speeds. And finally, we're also enabling more customization for full text indexes and search, starting with custom stop words. So if you're familiar with Lucene, you can choose a stop word list for how you want certain stop words like the, onto, and other words that maybe would add noise to your search. But in some scenarios, you may want some stop words included as well. So we're giving you the ability to customize that just like you can on Lucene. Now, we're also extremely excited to talk about this. Cosmos DB is building a hyperscale vector search offering called Azure Cosmos DB Garnet Cache, built on the Garnet stack from Microsoft Research. It offers extreme high throughput. Think that you can index billions of vectors with millions of queries per second on a node. It features extreme low latency for those scenarios where speed really matters, where vector searches will complete on the index in under 10 milliseconds. Of course, it's Cosmos DB under the hood, so it's highly available and is able to scale up for throughput needs and scale out for your indexing needs as well. There's a QR code in the bottom right-hand side and an AKMS link. You can sign up to try the Azure Cosmos DB Garnet Cache preview. And then finally, we also launched at Ignite the Azure Cosmos DB MCP Toolkit. So MCP servers will be the premier way for agents in Microsoft Foundry Service to interact with various other services external to your agent, right? And Azure databases are no different. We've brought a MCP server that you can host yourself in an Azure Container App to be the interaction point between your agents in Microsoft Foundry Service and Azure Cosmos DB. So you can enable retrieval scenarios and semantic search and more. Okay, so we talked about Cosmos DB and some of the new stuff. Now let's hear about Cosmos DB put into practice in production today. I'm going to hand it off to Zach Rossman and James Nguyen.
Thanks, James, for the great intro. Hey, everybody. My name is Zach. I am the tech lead for our AI and security team at Veeam Data Cloud. I'm going to be talking with James today.
My name is James Nguyen. I'm a cloud solution architect at the customer success organization, working alongside with Zach and Veeam to build this solution.
So this whole thing started back in April. We sat down with James, and the rest of the Cosmos database team to build next-gen search for our Microsoft 365 protection workload at Veeam Data Cloud. Just a quick overview of Veeam. We are recognized as the leader in data resiliency across industries. We have over 500,000 customers, and 77% of the Fortune 500 depends on us to protect their enterprise data and infrastructure. So that is to say we're working in very high scale, high stakes engagements here. Veeam Data Cloud is our managed service offering, and what that means is that customers don't need to themselves manage and provision the infrastructure for each of these data protection workloads. And on top of the traditional backup recovery, data portability features that they've come to know and love, we also have data security, data intelligence offered through a modern web UI, a single pane of glass, like we like to say. And Microsoft 365 is one of the fastest growing, most popular offerings in this portfolio. We back up billions of items every day, petabytes of data every day, and customers love that they can pick from any one of 23 Azure regions to determine where their data is going to be processed and persisted. But one thing that repeatedly comes up is that our search, our data discovery, it's really brittle and it's inefficient at scale, which is a problem especially for our enterprise customers. So what James, Microsoft, and Veeam sat down to do is build next-gen data discovery. And so what this really boils down to is hybrid search. So of course we need scalable filtering on the item metadata so that if you have precise criteria that you need to be able to find your backed up data for, you can do that. But on top of that, we also have semantic search on item content. And that means if you have the content of an email that you kind of have this fuzzy memory of, or content of a file, you can actually search for that without needing to recall the actual keywords or parameters for that data. All of this is offered through a natural language interface, and then we offer multilingual support. And that's important because Veeam has customers spread around the world, tons of different languages, and it might be the case that enterprises are so big that the data that we're protecting is different from the language that the actual operator in VDC speaks. So if they need to find data in a different language, this is meant to help them. And then of course, how we build it, security is always top of mind, scalability as we talked about, reliability so that customers know if they back up data, they can recover it. It has to be regional because we need to abide by data residency requirements, and we also don't want to pay data egress charges between Azure regions. That feeds into the cost efficiency, and then our team is lean and mean, so we need to have low operational overhead for the entire system. For some of the underlying pillars for this system, it's an event-driven architecture, so we have Azure Event Hubs, which is great for low latency, high throughput events. For the basic compute, think like API services, we're using Azure Container Apps. And then for more of the data transformations that might be parallelized, this happens in Azure Databricks, sitting on top of Azure Delta Lake. And then we have, of course, Cosmos Database, which is where our vector data, it's what we use for our vector database, where the vector is stored next to the metadata. And we're using Azure OpenAI service in two ways. First, to generate the vector embeddings with the text embedding 3 small model. And then we're using the chat completions API to actually dissect the natural language prompt into its component parts for the database queries. We're going to talk about the architecture in 2 parts. I'm going to talk about the basic metadata indexing pipeline, and James is going to deep dive on how we build semantic search. So on what would be, at the very start of the pipeline are our data publisher services. These are our backup engines. And what they do is they publish the full content and the metadata for the billions of items that we back up every day. They publish those to the data extractor services. This is like an interface between the workload-specific data formats and the rest of our engine, which we are building to be workload generic. And this means that every time VDC onboards a new workload, we expect these capabilities to extend to those new ones. We have a data versioning service so that you can keep track of which items and which content was available at what time in your system. And this is underpinning our entire story around granular data recovery. The data is stored in Azure Delta Lake, and then we use an API service that actually uses Azure Databricks SQL Warehouse to run scalable metadata filtering directly from Delta Lake. As you'll see, I didn't mention vectors, vector search, semantic search anywhere in here. That's what James is going to talk about.
Yep. So I'm going to provide some more details about the architectures of how Veeam was able to achieve this massive scale vector search. So again, from the left, We start with the event-driven ingestion layers. So when backup jobs land new data from customer to the Azure cloud, the data publisher services send batches of reference for new and change backup items into Azure Event Hubs. And then data extractor services then pick up those events, read the raw content. For example, if you have email files, the metadata can be like recipients, senders, date sent, and then the content of the emails, right? So for the metadata, they get sent to Event Hubs, while the content lands at the blob storage. So this first stage is a classic event-driven pipeline powered by, like Zach mentioned, Azure Community Service and Azure Container Apps for scalable compute. So this is pretty straightforward. Then we move to the second stage, focusing on merging and refining and enriching the data. This is a very heavy operation, very expensive. So we use Databricks as a compute engine. So the first step in this second stage is that the data versioning service, which is a data streaming job that ingests data from the Event Hubs and perform large-scale data mergings on top of data lakes, right? So this is very scalable because of the distributed compute and streaming's capability of Spark. And then after data is merged, the next step is to perform the content refinement, where Apache TK is used to clean the content, do the OCRs, and then perform further metadata extraction. And then data goes to the next step, which is the enrichments. This is a lot of innovations happen here. First, like keywords are extracted, the contents are summarized. So these things will serve as the important elements for rich search experience later on. And then in the last part of this is like the Databricks also send data over to Azure Embedding Service to vectorize the data. So the clean, enriched data now land in the Go layer of the Delta Lakes for long-term storage and metadata discovery. The last step in this is advanced indexing service, where Databricks uses Spark Cosmos DB connectors, which is a very high performance connectors to send data in bulk to Cosmos DB for indexing. So one thing to highlight here is that this entire pipeline, the Spark with the shuffling capabilities balance across the tenants, so that very large tenants don't slow down small tenants. So this is pretty relevant for Veeam, especially when it comes to multi-tenant data pipeline like this, right? So you can have noisy neighbor, and this is the key, one of the key criteria to select Spark for this pipeline processing. And one thing to highlight here is that this entire architecture is co-located to every Azure region where customer data reside. So this delivers the compliance for Veeam. Right, so on top of the Cosmos DB semantic search, Veeam builds an intelligent discovery service, like mentioned. Basically, this uses agentic AI to translate the natural language query into structured technical queries, so that users of this system, they don't have to know about the schemas, the structure of the database. They just use natural language, and then the intelligent data discovery service can run the query and return. So, and also, Veeam exposes as a MCP service, so it can be ready for agentic AI consumption. So I like to hand off to Zach to talk about Cosmos DB schema design.
Thanks, James. So we're going to do a deep dive on what it took to actually implement Cosmos Database, which again is just one small part of this entire pipeline, but it's critical. It's what serves the semantic search capabilities. So this is more or less what our document design looks like, a document being like an atomic unit in a Cosmos Database container. So it boils down to really storing item metadata along with the vector embedding. Cosmos Database, like other NoSQL databases, enforces a max size on the documents. This is set to 2 megabytes. The vector embedding, based on the settings for the embedding model we use, text embedding 3 small, we get 1,536 dimensions, each of those being a float 32. And so that is stored in the vector embedding field there. One key constraint that we had to design around that everyone building on Cosmos Database needs to consider is that there is a maximum size of 20 gigabytes per logical partition. And a logical partition is just, again, a logical grouping of documents in a particular partition. And so if we had put all of the data for a given tenant in a single logical partition, we would hit that in like a day. And so what we had to do is we used the hierarchical partition key feature from Cosmos Database, and we have a three-part partition key. We have a synthetic first-level key, being the tenant ID and the data type. Then we have the item owner identifier, like whose data does this belong to within an organization. And then we have the item ID. And we actually work backwards, you know how with NoSQL schema design, you're supposed to work backwards from your data access patterns. And so what we said is, we know we need to run searches for particular item owners. We know we need to run searches across an entire tenant for a particular data type. And so this is how we kind of reverse engineered or backed into this schema. And we added the item identifier as the third level partition key because if we only had 2 levels, we were not confident that we would fit within that 20 gigabytes. But now adding the item ID, that means our data is sharded effectively across this many logical partitions. Once we have the logical partition constraint figured out, we need to understand how this data is organized in the physical hardware at the infrastructure layer. So Cosmos Database has physical partitions. You can see that we have documents within logical partitions and logical partitions within a physical partition, each physical partition having a max size of 50 gigabytes. And so again, you'll say like, aren't we gonna run into that 50 gigabyte limit? Well, what happens is when our advanced search indexing service, like James mentioned, we're using the high throughput Spark driver. When it is indexing documents at particular logical partitions, Cosmos Database does the mapping between logical partition and the physical partition. And if we get close to that 50 gigabyte physical partition limit, it's actually going to seamlessly horizontally scale under the hood for us. We don't need to have an operator say, create a new cluster. We don't need to index it at a different point. All that stuff would add to either operational complexity or complexity in our application logic. We like to keep things simple at Veeam. So what Cosmos Database does for us is it has this, again, low operational overhead, but quote unquote infinite scaling capability for us. And then you might say, well, even if the horizontal scaling is covered, aren't we gonna have to scan all that data when we're running searches? But the point of the hierarchical partition key is that you can narrow your searches based on what partition keys you provide in the search. So as long as we provide the tenant ID, the data type, and the user we're searching for, we can narrow down our search to a very limited space within these physical partitions. And this saves us on RU costs, and it decreases the latency for these searches. James is going to talk about some of the underlying tech that Cosmos built to make this possible.
Right. So we talk a lot about vector search as the key capabilities in this platform. Lots of search engines have vector search, but they are not created equal. To enable efficient searching at these scales, we employ sharded DiskANN vector search, originally developed by Microsoft Research and now right into Azure Cosmos DB. So DiskANN is a graph-based approximate nearest neighbor algorithm designed for massive data sets. It combines the graph building algorithm with product quantization to compress vectors, so it can search billions of data points efficiently. The key innovation is that it stores most of the index on fast SSDs while keeping the compressed pointers in RAM for quick access. So this combination gives us the high accuracy and low latency and the ability to scale far beyond what in-memory approaches can handle. So now with sharded DiskANN built into Cosmos DB, we take that performance even further with the large-scale multi-tenant scenario that Veeam is dealing with. When you set a vector index shard key in your container indexing policy, Cosmos DB automatically creates multiple DiskANN indexes, one for each unique shard key value. So that delivers several key advantages. Number one is low latency. So each tenant index now is smaller. So search is complete up to 91% faster, according to research from Cosmos DB team. And it reduces cost because smaller indexes use less compute, cutting IU consumption by as much as 85%, and improve recall, right? So focusing on, because most of the time you just search I mean, in Veeam's case, user only search within their own tenant data, right? So first, focusing on the right tenant data makes the result much more accurate with the recall gain up to 12%. And then better scalability, right? So when we need to add more tenants, it's just a horizontal scaling, so which is natively handled by Cosmos DB. And finally, the tenant isolation, right? So each tenant, they're gonna run on their own search index. So all of this empower Veeams to deliver low latency, cost-effective search on their massive data set.
Thanks, James. We're going to deep dive on cost optimizations also because we need to make this financially viable, not just for Veeam, but for our customers. So we're going to go back to the original document schema that we talked about at the start of the presentation. Again, we have the metadata and we have the vector embedding. The vector embedding, when we broke this down, the document consists of basically 1 kilobyte of metadata and 6 kilobytes for the vector embedding. And when we did a cost analysis, we found this was not going to work for us because we have to pay for RUs to insert, we have to pay for the data that's stored at rest in Cosmos database, and then we have to pay for RUs to retrieve the data. So I'm not going to say you get hit for the size 3 times, but it's a consideration in 3 of the different places that we get billed. And so what we did is we worked with the Cosmos database research team, James, and we figured out how to reduce the size of the vector embedding down from 6 kilobytes to 1 kilobyte. And what we did is first of all, in the Azure OpenAI API, you can request a fewer amount of dimensions. So instead of 1,536 dimensions, you can request 1,024. And then we also quantized the dimensions themselves from float 32s into int 8s. And so altogether, if my math is correct, this comes down to 1 kilobyte, and it effectively reduces our cost by over 5x for Cosmos database. No, 1 slide too far. We are actually going to demo this now.
2.
To 2. All right.
Okay.
All right. So this is a look at the Veeam Data Cloud admin console. We are on the demo Wi-Fi, so hold tight. I'm going to pick the org that has this. This is our code name for the project, Project Atlas. Once we arrive here, you'll see how we kind of have a portfolio of workloads. This is what we're talking about, where we have Entra ID, CASN is our infrastructure backup product. We have Salesforce, but we're going to work with Microsoft 365 today. We're going to go to the particular instance of Microsoft 365 backup. This itself lives in Germany West Central region. Okay, and this is what customers will see when they're trying to administer and see how their data is protected in the Veeam 1 UI. We're going to go to our search portal here, and what I have right now is we have just a single item owner, let's say for this demo use case, and that corresponds to this Outlook mailbox that you can see here. So this is my colleague Sesha. He's a big fan of the TLDR engineering newsletter, and so I don't know, let's say his mailbox got corrupted and he really needed to catch up on his TLDR content. And again, this is a progressive demo, so we're going to start slow. This is just typical metadata search where you can search for certain properties like who sent the data, etc. There's nothing groundbreaking there, but the whole point is that this is scalable metadata filtering, which Veeam didn't have before this project. Let's branch out here. So I know Anthropic had a big announcement this week. But what I think that happened on like the 18th with Microsoft. So congratulations. Let's search the newsletters to see what we had at that date. So at that snapshot point, there were no emails that had Anthropic in the subject. But let's say we wanted to search the data on the 19th. I think that's the day after Satya announced it. All right, here we go. We have Anthropic with a new raise. Great. And that's just the metadata filtering portion of it, but let's up the ante here a little bit. Let's get into some non-deterministic demos. Let's say I want to search, so this is our natural language search interface. Let's say I want to search emails from our CEO. Okay, so this is Anand's email, and what's happening here is Azure OpenAI is deconstructing this query right here and mapping my intent to an actual database query in the back end. One thing I love about large language models is they understand the context around your query. So even though I was asking for emails from Anand, let's say I wanted emails from today, and I was like a little bit imprecise about what I was searching for. Azure OpenAI knows that I'm talking about a received date, even though I was previously talking about a from, like the sender of the email. I notice here, okay, this was actually from yesterday, but it's because we're using UTC time. What if I try specifying the time zone? And you'll see the results are actually filtered even further. And this is just kind of the magic of generative AI for these natural language queries. If I wanted to change the time zone, let's say I wanted, I don't know, Eastern time for some reason. Again, we have from the 19th, but in EST time, this is technically yesterday. So you can really have some fun with the different cases here. But let's say, again, I promised you semantic search. So let's look at this email in the inbox. This is talking about how Bitcoin price is crashing. I hope all your portfolios are doing okay. If I search for crypto price trends, like this doesn't have any keyword match to that email. Outlook search cannot find it, and it mentions because we don't have a keyword match. But if we go to the Veeam semantic search site, we'll see this email comes to the very top of the list. And that's because it's not matching on keywords. It's vectorizing the content of the email, vectorizing the content of the query, and running a vector search behind the scenes. If we wanted to search for like the latest OpenAI model release, okay, we have the 5.1 release in here. We don't discriminate between model providers. Let's talk about like Gemini 3. Okay, pulls that up fine. You'll notice Google is not mentioned in the metadata here, but it's mapping the content of this email, again, to a vector and running a vector search under the hood. Another thing, let's go back to our crypto example. What if I'm a French admin? Yeah, okay, so crypto price trends. I think I searched originally in English. Here we're gonna search in French. And you can see the same email comes up because the vector embeddings are multilingual, fundamentally. So this is the demo. Thank you so much to the Veeam team who made this happen. And thank you, James and Microsoft, for having our backs here. All right.
Awesome. Thanks, guys. Yeah, it's really cool to see it live in action, right? Like we talk about vector search, we talk about vector embeddings and advanced search technology. It's really cool to be able to see it in practice at enormous scale. Okay, so let's switch over here. We're going to do a preview of our semantic re-ranker functionality in Azure Cosmos DB. So this service uses AI to improve the search relevancy of any of your query results. So imagine this simple pipeline where maybe you have a chat application or a search application like what Zach was showing here, is you have a user asking a question and you take that question and you form a query out of it. So imagine that you're creating a vector search or a hybrid search query, right? You create a vector embedding of your search phrase, and you run a vector search on your database to find the most relevant results according to the vector embeddings and your similarity score. Well, semantic re-ranker can take additional context into account and feed it to a specialized AI model that will reorder the search results for improved relevancy. And so you essentially will get, in many cases, the results in a different order, where the more relevant results will be at the top of the list. And this is useful for multiple different reasons, right? In a search application like Veeam, you want the user to be able to find the content that they're looking for more quickly. In generative AI applications or agentic applications, you want to be able to maybe search, you want to be able to cast a wider net on the material that you're searching for, and then maybe find the top 3, 5, or 10 items that are really, really most contextually relevant for your large language model. And the semantic re-ranker can help you do that. Now, right now it's an early private preview. You can go up to the AKA MS link here and sign up for it, or you can scan that QR code and it will take you there. So let me switch over here and I'll show you a quick demo of what this looks like. All right. So here I have my VS Code open. And what we're going to do is I'm just going to show you how easy it is to call the re-ranker service from Cosmos DB. So we have some initial setup here. Basically, we're just connecting to our Cosmos DB resource using the Cosmos DB SDK and our Azure OpenAI embedding models using the Azure AI SDK, right? And so we have a helper function here for generating the vector embeddings. So in this scenario, I've loaded a Cosmos DB container with a bunch of customer support tickets for an imaginary company that builds applications for supply chain and logistics, right? And so for conducting a semantic search on my database, I need to do a few things. I have to vectorize my data, my relevant data, create vector embeddings of it, and store that in Cosmos so I can search over it using DiskANN. And then when I have a user that asks a question, I need to vectorize their search phrase and execute my semantic search. So this helper function here is just for doing just that, generating the vector embeddings for my search. So imagine that imagine that I want to find customer support tickets that are related to a new ticket that was opened, right? So this one just says something simple. My app isn't connecting. It's preventing me from getting the data that I need. And maybe we want to add some other details as well. So I only want to see like the items that are resolved. So what we'll do is we'll convert this into our vector embedding and we'll do a semantic search over it. So in this function, we're doing a hybrid search, right? We're selecting top relevant results and we're projecting our similarity score here. So this is our cosine similarity that we're using. And then we're doing a order by clause at the end, right? So we're ordering by the rank of RRF. So RRF is our fusion method for combining vector search with our full text score, which is a statistical measure of the frequency of terms in our search phrase, right? So the more often that terms appear, the higher importance of those terms in the documents, in these support tickets, the more likely they are to appear towards the top of our search results. So we have this helper function here just for executing that search. And what we'll do is we'll go ahead and ask for the top 20 results here. And it comes back fairly quickly, even though we are on the demo Wi-Fi and have to deal with the constraints of multiple other demos here. Well, what we can do then is we can look at all the results that come back, right? So here's one customer support ticket. I have difficulty syncing my data between the app and our ERP system. And what's cool is in this data, I also have other sort of relevant information, right? I don't just have like the subject and the description, but I have maybe the conversation between a human and an agent for resolving this step, right? This problem. So I can see all sort of the associated metadata here and the semantic similarity score. So here I ask for the top 20 results and I have 20 of these results to sort of go through. So what we're going to do now is we're going to call the semantic re-ranker service using the Cosmos DB Python SDK, right? So on our container, we're going to call the semantic re-rank function. And here we feed in a couple of parameters. So we're going to add the search string. So this is the search phrase that we had, but we can add any other additional text context to this as well, right? So imagine that you are talking with your customer and maybe you have some previous historical context of other tickets you've worked on or other pieces of information in the chat history, right? You can bring that into the context as well. And then for documents, we'll pass in the results from our search and we'll ask it to do this re-ranking and we'll return the top 10 most relevant results. And then we'll take a look at like what the results look like here, right? So we're printing out a couple of things. We have the index. So this is the index number of, in the original hybrid search, what order did this original document appear in, right? So we see index 4, so it starts at 0. So this is the 5th element from our search results. So this was in the 5th place of our search results. And now we see that it's the first item at the top of our list. Right, so the AI-based re-ranker determined that it has a high relevancy score to our original search result and re-ranked or reordered the results for improved relevancy. And what we can see is repeatedly, time and time again, is that the re-ranker will help you find the most relevant results and bring those to the top of the list. And we see this in multitude of use cases across different domains. And this re-ranker model is time tested and verified. This is the same re-ranker model that was developed by the Azure AI search team that delivers world-class re-ranking to existing customers, and we're bringing it to Azure databases and for the first time in Cosmos DB. And like I said, it's really easy to call just from the SDK, and you can add this to all of your search workloads as well. Okay, so that about wraps it up for us here. You can check out some additional resources. So we have a great blog post that goes in depth about the content that you heard here from Zach and James. We have some articles on how you can get started easily with semantic search in Cosmos DB. On the right-hand side, we have sign-up forms for all the previews that we talked about today, the semantic re-ranker, and the hyperscale vector search offering Azure Cosmos DB Garnet Cache preview. Next, we have a lab that's starting in about 30 minutes here, led by one of my colleagues here, Theo, that's going to talk about building multi-agent applications in Azure Cosmos DB. And of course, you can always come and chat with us. We'll give you some Cosmos DB swag for some questions, and we can go from there. So thanks for joining us today, folks. We'll hang out a little bit in case there are questions, but have a good one.